Section 3.4, properties of logarithms. We are going to carry forward a little bit further what we know about logarithms from the previous chapter, or the previous section. So far, all we know is basically what the graph of a logarithm function looks like. We know that a logarithm is the inverse of a exponential function, and we also know how to take a logarithmic or an exponential function and change back and forth between those two forms of equations. Okay, so to start off this section, we are going to talk about how to take a logarithm and change the base to a different one. We have what you could say is two standard log bases. The first one is the common log. It has a base of 10, and usually the 10 isn't written, and so we just say log of x. Then we have the natural log. It has a base of e, and e is approximately 2.71. It's an irrational number, but with the base of e, we write ln of x. And these are two standard buttons on most any scientific calculator. Okay. The TI that I use in class actually has a log base function where I can change the base of a log function. But some calculators don't have that. They only have these two standard ones, common log and natural log. And so it's very helpful to be able to change from a log with a base of perhaps 2, or any other base for that matter, log base 5. More than likely your calculator doesn't have these logs with these particular bases, and so that's where this first part of this section comes in. Okay, it tells us how to change the base to go from a base of 2 or 5 to one of the standard ones, 10 or e. Okay, so here we have a series of logs, logarithmic expressions, and they're all equal. And so on the left we start with log base ax. Well, if we don't have a calculator that can change the base, then what we can do is change the base by writing log of b. Okay, and b just sort of, it could be any number. Perhaps we don't want to change to one of the standard ones, 10 or e. Then we could pick out any base number as long as it's greater than 0. And we could write log with the new base, b, in the numerator and denominator, and then simply use the argument and the base as the argument in the numerator and the argument in the denominator, respectively. So for instance, just to take one of the examples over to the right that I mentioned, say we wanted to change from a log base 2 to a log base 5, then we would simply write log with the base 5 in the numerator and denominator, and then we would take our original argument x, use it for the argument in the numerator, and then take our original base 2 and use it for the argument in the denominator. Okay. Then likewise, we could switch to a base of 10, or in this last expression, base e. So example 1, that's exactly what we're doing. It says use the change of base formula to approximate the following. Okay, and a lot of the logarithmic expressions turn out to be irrational numbers, and so by approximate, that simply refers to the fact that we're going to have to round the output at some point. Okay, we can't write out all of the decimal places. So let's take a look. I'll bring up my calculator. And as I mentioned with this particular one, TI-84, I actually have a function under the math menu, log base, to where I can enter in any positive number for my base. Let's see, our first example is log base 2, and then the argument is 23. And so really nice, I can just calculate it that way. So I could approximate it to, let's say, 3 decimal places to the right of the decimal point, 4.5 to 4. So doing it that way with my calculator, I actually didn't use the change of base formula. So if you have a calculator that can't do that, you would need to use either the common or the natural base. So let's say we used the common, log base 10, and I don't have to write the 10, that would be understood. And then we want to use the 23 as the argument of the numerator, and then the 2 as the argument of the denominator. And we'll calculate this expression and see how it compares to the original one, the one that you would probably consider to be more accurate. Let's see. Here's our 2 standard log bases, and so I would simply write log 23 and then divided by log of 2, enter, and we get 4.5235. And so if I round this to 3 decimal places to the right of the decimal point, we get the exact same number. Alright. And so with my calculator, what I'll do is I'll calculate it the other way with the log base function so that we can compare more decimal places. So I'll enter 2 for my base again and 23. And it's exact. They're exactly the same number all the way out to 3, 6, 9 decimal places to the right of the decimal point. So it's an equivalent way to calculate the same expression. Okay, so here's another example. We have log base 5 and the argument's 367. We could use the natural log this time to approximate it, and we can write ln, and you can see that the 365 spatially is oriented above the 5. The 5 is a subscript of the log. Okay, the 5 is a base. So that should remind you as to where the 367 actually falls in reference to the fraction that we're about to make. We have a numerator and denominator. 367 sits above the 5, so 367 would be used as the argument in the numerator, which is above the denominator. And then the 5, the base of our original expression, goes into the denominator. Likewise, we could have used the common log. log of 367 divided by log of 5, and any other base for that matter, except now we would have to actually write in the base number that we were switching to. I could switch this to a log with a base of 2, but whatever base that you're switching to, you want to use that base in the numerator and denominator. And so once again, 367 in the argument of the numerator, and 367, or sorry, not 367, but 2 in the denominator. Or 5, I'm sorry. 5 was our base. So 5, base of the original expression, would become the argument of our denominator. If you enter any of these into your calculator, you will get the same exact result. So first I'll calculate it using the log base function under the math menu. I can put in the exact base and the argument, and we see that we get 3.66920767. So what do we get for these other three? The first expression I wrote with the natural log, so ln of 367 in the numerator divided by ln of 5 in the denominator, and we get the same output, 3.66920767. What about the common log expression, 367 in the numerator, 5 in the denominator, and once again the same result. And now for log base 2 of 367, just to show you that I can switch to any base b, as long as b is positive and 2 is positive. For this one, I'll have to use log base function. So with a base of 2 on the top, and once again on the bottom, base 2 and 5. Okay, I have an extra parentheses here. Let's see. I'm going to delete that one. Delete. Okay, something's going on with my parentheses here. So if your parentheses are messed up, you will definitely get a different output. So let me try that again. I'll remove that calculation, and I'll go back to my log base. We have 367, and we have 2 for our base, divide. And I think the problem showed up when I used the log base function. It automatically put in some parentheses for me. But just make sure you're careful with the parentheses. Okay, so they're already given to me. I don't have to put in my own. I just simply enter the base and the argument, and there we go. Okay, I finally entered it into the calculator correctly, and we get the same result as we had before, 3.66920767. So any of these expressions, any of these logs with the different bases, are equivalent to this original expression, log base 5, argument 367. So I will write, I'll round it to the nearest thousandths, 3.669. Okay. Um, C, we have a fraction as the base, okay, of the original expression. So A in this case is 1/3. And if you reread the change of base formula instructions, it says that A and B, which are used as bases, any number is acceptable as long as it's positive, as long as it's greater than 0. And also, we don't want A and B to be equal to 1. So 1/3 is acceptable as a base. If we want to approximate this with the common log, then we would write log of 16 and log of 1/3. And here again, the base that I'm switching to is 10. I have a base 10 on the top and a 10 on the bottom. This is just understood as the common log, so we don't write the 10. So I'm switching from a base of 1/3 to 10. Let's see what our calculator gives us. If I write log of, let's see, 16 divided by the log of 1/3, enter, I get negative 2.53, or I'm sorry, negative 2.523719014. Okay, so I'll round this to the nearest thousandths, negative 2.524. And again, I'll calculate it with the original base of 1/3 and the argument of 16. And again, we get the same output, negative 2.523719014. For D, we have a decimal for our base. And so the only question you really need to ask yourself about the base is the base we're given positive? In this case, we don't see a negative sign, so 0.53 is an acceptable base for a log function. We'll use ln. And again, we could use log, ln, or any other base for that matter, but I'll just use ln for this example. And so we would write ln of the original argument on top, and then ln of the original base on the bottom, 0.53. And we pull up our calculator and let's see what we get. We have ln of 16 divided by ln of 0.53, negative 4.367 if I round it. And now we'll see what we get if we use the original base of 0.53 with the log base function. Okay, log, enter my base 0.53, my argument is 16, enter, and we get the same result as the previous expression with the natural log instead. So again, negative 4.367 if we round to the nearest thousandths. So the change of base formula should come in very handy if you happen to have a calculator that doesn't have a change of base formula already programmed into it, or perhaps it does and you just don't know how to use it. This gives you an alternative way to approximate the log with any base. So more properties. Again, we're told that we have a log function, and a is our base. If you look at the properties that were given below, in each case of the log function, a is our base, and so once again we want a positive base, and then we do not want a base of 1 for any of our log functions. And so we have 1, 2, 3 different properties that were shown here. Okay, and what they're doing is they're showing us a different way that we can write the log function if our argument can be written as a product. So for instance, up above, log of 1/3, base 1/3, with the argument of 16 could have been written as an argument of 4 times 4. So the argument 16 is rewritten as a product. And that's what the u and the v are. Okay, they're the factors of the product. So as in this case, u and v would be 4 and 4. They would be equal. We could have factored 16 any way that we wanted. We could have written 16 as a 2 times an 8. And so this property is simply referring to this situation where we change the argument in terms of factors. And if that's the case, then we can write separate log functions for each factor as long as we add the two log functions together. So in this case we could have written, and we keep the original base that we're given for each log, 1/3. So I can split it up in terms of the factors. I can write log base 1/3 of 2, and I can write log base 1/3 of 8. And if we started out with a product of those two arguments, then you would add the two log expressions. Okay, the second property, you can see that the argument is written as a fraction. In that case, you can split the numerator and denominator apart and create separate log functions for each. Okay, keeping the original base a, but then if the numerator and denominator, okay, they were originally divided, we have to subtract the resulting log expressions if you separate the numerator and denominator. So this concerns division inside of the argument. And then third, if we have an expression in our argument of the log function, any number raised to the n power, then what we can do is simply write the log with the original base of u, and just pull the exponent of the argument out to the front and multiply it. So for instance, up here on top we had we could have written 16 as 4 squared. Okay, if you square 4 you get 16. So these two expressions are equivalent. And using the third property, we could say that the exponent of our argument is 2, and we could rewrite this as 2 times the log with the base of 1/3 of 4. So with this exercise 1, it's merely wanting to point out the fact that this base could be any base, and the properties that were listed, property 1, 2, and 3, would still apply. So we could rewrite these properties with respect to the common log or the natural log or a log base 2 or a log base 5. As long as the base is positive, then these properties will apply. So I could write the first property as log of uv equals the log of u plus the log of v. Likewise, I could write ln of uv equals ln of u plus ln of v. For the second property that involves division, if I had the log of u divided by v, then I could write the log of the numerator first, u, minus the log of the v. Okay, keep in mind subtraction, the order of subtraction makes a difference. So the log of the numerator must come first, and then we subtract the log of the denominator. Using ln instead, ln of u divided by v could be written as ln of u, which, well, that looks more like v, ln of u minus ln of v. And then finally, for the third property, with a base a of 10, we could write log of u to the nth power and simply bring the n out front, whatever the exponent was, and n would multiply this log function, leaving u as our argument with no exponent. Okay, the exponent was swapped out to the front, and it's now multiplying the log. Likewise with the natural log. Okay, natural log of u to the nth power could be written as n times the natural log of just a u. And now our exponent of the u would be understood to be 1, as it was with the common log. Okay, so let's apply these properties to rewrite these expressions in example 2. Okay, here it's just simply saying that our base is b, okay, and our factors would be any number or variable x, y, z, and w. Alright, and so we want to break up the factors, okay, into separate log functions. And in each case, we want to just simply use, for each log expression that we break the original one up into, we want to keep using the same base, b. So with a of example 2, we have a base of 3. So any other log function that we write out to the side will also have a base of 3. Okay, what is happening with the 9, the x squared, and the y to the third? Well, they're being multiplied. Okay, all of these, we basically have 3 factors here of our argument. And whenever the argument has multiplication contained inside of it, then we break it up into addition of each factor. So we could write log base 3 of 9 plus log base 3 of x squared plus log base 3 of y to the third. And now we could go a bit further and say, well, the log is simply just asking the question, what exponent do we raise 3 to get a 9? And that would be 2. Okay, we can actually calculate this one. And then the second expression in our sum can be rearranged using the third property, because the argument now has an exponent of 2, and from the third property we see that we can simply bring the exponent down in front of the log, multiplying the log. So the exponent 2 would come to the front, and it would multiply log 3 of x. And likewise, y has an exponent of 3, and we could bring the exponent down in front of the log, multiplying the log 3 of y. And at this point, this is pretty much as far as we can take it, but we have followed the instructions of breaking the different parts of the argument up with respect to log of x, log of y. Okay, and that's what we have. We have log 3 of x, log 3 of y. So b, we have a different base and definitely a different expression. In this case, we have a radical contained inside of our argument. And so before I get started trying to break these components of the argument into separate log expressions, I want to remind you that the square root of w can be rewritten as w to the 1/2. And so we don't have to have a separate property for log functions in regards to radicals. Okay, that's already taken care of with the third property, the property involving exponents. So the x and the w are multiplying one another. We can write those as the sum of the two separated. Oh, that should be a 7, not a z. So this is our base 7. Argument w to the 1/2. And now the z is dividing those two. And so in terms of log base 7 of z, we would subtract it because z squared is in the denominator of the fraction. So we would write log base 7 subtract log base 7 z squared. So what we did with the x and the w is we applied the first property of logs, and then with the z squared we applied the second property. So this is property 1, and this last one we subtracted as a result of property 2. And now we'll go back through, since our arguments have exponents, and we'll apply property 3, which tells us to just take the exponent of the argument and bring it to the front of the log. So log base 7 x to the third would become 3 times log base 7 of x. The 1/2 of the w would be brought to the front of the log. And now for the z squared, we would bring the 2 to the front of the log. I keep wanting to write that 7 as a z, but the base would stay 7. So 2 times log base 7, and then with just a z. And at this point, the exponent of the x, w, and z is understood to be a 1 in each case. And so we've taken this expression and we've broken it down to about as far as we can go. Okay, we've broken up the different variables into their own separate log function. Okay, so log, and here's our expression. We have log, and notice that we aren't given a base. There isn't one written. So with just log, it's understood that the base is 10. Okay, so you don't need to write the 10 there. I just wanted to point that out. And here we have a numerator over a denominator. We have division inside of our argument. So in this case, we could apply property 2 and write log of the numerator, and with division we subtract. Numerator comes first, and then we could write log of the denominator. Each log that we broke the original up into carries the same base, 10. It's the common log. And now what was the numerator? Well, it was the expression 2x minus 1, and then the denominator was z plus 2. And you may be tempted to try to write this log separately in terms of x, and then this log separately in terms of z, but we weren't given a property that involves subtraction and addition. Okay. The arguments of our properties were multiplication, division, and exponent. So this would be as far as we could go in terms of rewriting this expression using our properties. D, we have a product in the numerator. This is x times y, and each have their own exponent, and then we divide by z. So the x and the y on the top could be broken up into separate natural log expressions. An ln of x, and the two would be added since the x and y are multiplied, and so we'd get an ln of y to the fourth. And with the z dividing those two, the z being in the denominator, we subtract the natural log expression for the z. So for x and y, we applied the first property. For z, we applied the second property. And now some of these variables involve exponents. We apply the third property, and we would get 2/5 times ln of x plus 4 times ln of y minus ln of z. And so that would complete example D as far as we can go. Example 3 says, suppose that we actually know the result of log base b of x, okay, and it's 2/3, and then log base b of y is 4/7. Okay. When we break up this expression here, we can actually compute it since we know the outputs for these different log functions. So we're simply going to apply these three properties that we know. We're not given a number for our base, we just simply use b, which is in line with the expressions that we were given in the instructions. So log base b and then the x and y are in the numerator and they're multiplied, so we could write log base b x to the third plus log with the base of b y squared. We've simply applied the first property where the product of two variables in the argument can be split up into two separate log functions in terms of addition. With the square root of z on the bottom, we could write log of the square root of z, subtracting it from the sum of the first two. And then again we apply the third one, simply moving the exponents of the argument down to the front of the log. And once again, this square root of z is equivalent to the log of z to the 1/2. If we bring the 1/2 down to the front, we can write it in terms of just log z, and our base was b. Okay, I left out the base in the original expression, but each of these logs would simply have the base that we started with. And now, being told that log base b of x is 2/3, I can write this first expression of the sum as 3 times 2/3. Log base b of y is 4/7, so I can write this expression, this middle part, as 2 times 4/7. And log base b of z, I was told, equals 5/2. So the subtraction on the end could be rewritten as 1/2 times 5/2. Okay, so I can actually calculate a number in this case. So let's see, 3 times 2/3 would simply be 2. Then we'd add to that 2 times 4/7, and then we'd subtract 1/2 times 5/2. We get a decimal, 1.892. Let me see if I can write this. I most definitely can write it as a fraction. I'll go to my math menu, select fraction, enter, and we see that this turns out to be 53/28. So this is just a instance of a type of problem that that could definitely be on the test. Example 4, it says use the properties of logarithms to rewrite and simplify each expression. Alright, so let's see, we've got 4 and 8. Okay. How could we rewrite this? Well, 8, I could rewrite 8 as a, let's see, I'll rewrite it as 2 to the 3rd power. Okay. We could have rewritten 8 in terms of an exponent as I did, or you could say 2 times 4, or you could have rewritten 8 as a 2 times 2 times 2, which is really the same thing as 2 to the 3rd. Okay, but having rewritten it with an exponent, I can now rewrite this as 3 times log base 4 2. And if you think about log base 4 of 2, it's simply saying what number do I raise 4 to get 2? Well, we take the square root. Okay, the square root of 4 equals 2. And a square root can be expressed as an exponent of 1/2. So we raise 4 to the 1/2 to get a 2. Okay, so I can actually calculate this without my calculator as long as you have a decent knowledge of some of the prime factorizations of numbers and some of the square roots of particular numbers. Okay, perfect squares like 4. I can rewrite this as 3 times 1/2. Okay, log base 4 of 2 is referring to this exponent. What do we raise 4 to get to? So I replace this entire log expression with a 1/2, and so we would just get 3/2 in the end. So log base 4 of 8 is 3/2. So let's try to do the same thing with b and calculate this without our calculator. Calculate it just by simply using the properties of the logs. Well, let's see, we have a different base. It's base 2. So I'll write this, and the 8 and the 3 here could be viewed as being multiplied. So I could write log base 2 of 8 squared. 8 and 3 are multiplied, so I could write a separate log function for the 3, but I would have to add it. Our base is 2. And now I separate the 3 to the 4th power from the 8 squared. I have to use the first property. Okay. For each of these numbers, I could simply bring the exponent down to the front. 2 log of 2, 8 is the argument, and then 4 times log base 2 of 3. Okay, and this first one I could calculate just by knowing, being somewhat familiar with whole numbers being raised to whole number exponents. 2 raised to the 3rd power is 8, so the log of base 2 of 8 would be 3. Okay, simply because 2 to the 3rd power equals 8. The log is basically a question asking what a particular exponent is. In this case, that exponent is 3. So this expression is simply 2 times 3. So the first one we turned out to get a whole number, but here with 4 times log base 2 of 3, we sort of run into a problem. If we want the exact answer, there's not much that we can do with this expression in terms of calculating it without a calculator. Because the log with base 2 of 3 is not a whole number. Okay, it's going to turn out to be an irrational number. And so what we could do is simply leave it written in terms of being an exact number. Okay, we could enter this into the calculator. we know that log base 2 of 8 squared times 3 to the 4th is this exactly. Or we could try to go a step further just to get a number out of it and estimate what this number would turn out to be. So this log expression simply asks the question, what do we raise 2 to? What exponent do we raise 2 to get 3? Well, if we raise 2 to the first power, we would get a 2. If we raise 2 to the second power, we would get 4 instead of 3, and 4 is greater than 3. So if you wanted to, you could sort of approximate it. You could say, well, I know the answer isn't 1 and it isn't 2. So more than likely it's going to turn out to be something halfway between 1 and 2. We could estimate it and say 1.5. Not really what the instructions told us to do. At this point, this sort of completes what we were told to do in the instructions. But if we just had to get a number out of this, we could say this is 6 plus 4 times 1.5, which is 6 plus 6. We should get about 12. Okay, so let's actually calculate it with our calculator and see how well we did at guessing. Okay, let's see. I'll write the original expression that we had using the log base function. We had original base of 2, and then as far as the argument goes, we had 8 squared, and that was multiplied times 3 to the 4th. Move that and enter. It turns out we were pretty close. A more exact answer is 12.33985. So with an answer of 12, again, we got pretty close. So with example 5, it says find the exact value of each expression without using a calculator. Okay, so you have to keep in mind we have to be given some nice numbers. We can't give an exact value if we have a log that turns out to be a rational number, as log base 2 of 3 did in the previous example. So we're going to need to rewrite things in terms of its prime factors, in terms of exponents and whatnot. So here we go with part A. Log base 2. I'll rewrite this as, let's see, this is the 4th root of 8, and so I can rewrite this without a radical as 8 to the 4th power. With 8 having an exponent now, I can apply the third property. Bring the exponent of 1/4 down in front of the log. And 2 and 8 are easy numbers in terms of a log function. Log asks the question, what do we raise the 2 to? Okay, what exponent should we have with a 2 to get an 8? 2 times 2 times 2. 2 to the third power is 8, so this works out to be 1/4 times 3. So we get 3/4 or 0.75, and this is an exact answer. Okay, if we pull up our calculator and use our log base function to use the original exponent we were given, 2, and then we write 8 to the 1/4 power, enter. Calculator gives us the same result. Okay, and it didn't round this at all. This is exactly 3/4 or 0.75. Okay, well, here's another expression. 2 ln e, and I'm going to go ahead and make some changes in this line with e being in our argument. It has an exponent of 6, which according to the third property of logs, I can bring down to the front and simply multiply the numbers that are there already, multiply the log, and so now I can write 2 times 6 ln of e. Log 5, well, two ways you could go about this. You can write the prime factored form of 125 using a factor tree. The number ends in 5, so we know 5 divides into 125, and it actually goes in there 25 times, and then 25 can be written as 5 times 5. So 125 in terms of prime factors is 5 to the third power. Okay, log, this is the common log, so our base is 10, and 1000 in prime factored form can be written as 10 times 100, and then 100 can be written as 10 times 10. So 1000 is 10 to the third power. Now, whenever we take the log of the argument that matches our base, okay, the base of ln is e, and so our argument matches our base. 2 times 6 is 12, but whenever the argument matches our base exactly, we just get 1. This is asking the question, what do we raise e to? E is the base of ln. What do we raise e to get e? Well, a 1. Alright, so 2 times 6 times ln of e is just 12 times 1. In the second, the next two expressions, we've rewritten the argument in terms of exponents. And so once again we can bring this exponent down to the front and multiply the 3. And we end up with a situation is same situation as we did with ln of e. The base matches the argument, and so log base 5 of 5 turns out to be 1. So this is 3 times 3 times 1. Now we subtracted, that's what we were given, subtract log of 1000, and we rewrote it as log of 10 to the third power. So this can be rewritten as 3 times log of 10. And again, common log is the base of 10, and so the base matches the argument. So this last expression is just 3 times 1. We end up with a 12 plus 3 times 3. This is 9. So 12 plus 9 is 21. And then we subtract 3 and we get 18. And 18 is the calculation of this expression exactly. Okay, we can actually type in all of this into our calculator. And compare it with our answer. So we write 2 ln, we need to write our natural exponential function e to the 6th power then we have plus 3. I have a different base, so I have to use my log base function, and I type 5 as the base and 125 as the argument. That takes care of this middle term, and then we have minus log of 1,000, and this is the common log, so I can just hit the log button and then type 1,000 for the argument and hit enter, and we get 18 exactly, the same number that we calculated. So you really have to be familiar with some of your perfect square numbers, your perfect cube numbers, and the prime factorizations of certain numbers. And a lot of these numbers popped up in intermediate algebra, and so if you hadn't taken that class recently, then you may not be as familiar with these numbers, such as 1,000 and 125. Alright, example 6, rewrite each of the following expressions as a single logarithm. So we're basically going to go backwards with our properties. So if you look at this long expression, we have the same base in each case, log base 3, log base 3, log base 3. So we can combine these into one logarithmic expression with a base of 3. Now, the first two log expressions are being added. But first what we need to do is take care of this 4 that sits in front of the second log expression. Okay, a number that sits in front of the log, just simply multiplies the log, can be written as an exponent of the argument. So we'll take care of our numbers in front of our log first. And we'll write this as a z plus 3 to the 4th power. Our third log expression has a 2 sitting in front of it, and so we'll rewrite it as a minus log. Okay, we'll leave the negative alone. We'll just simply look at that as subtraction. Log base 3, and we'll apply the 2 to the 2y plus 5 in the form of an exponent. Alright, now that we've went backwards and we found our exponents of the expressions, we can apply the multiplication and division properties of log, which say that if you have two things multiplied in one argument, then you can split them apart with addition. So we're going to go backwards. These two log expressions with the same base are separated with addition. So we can rewrite this as x minus 1 times a z plus 3 to the 4th power. So I combined the first two log expressions using property 1. And I've reduced this to 2 logs. Okay. These two log expressions that I have now are separated with subtraction. And if we go backwards, we simply write the arguments of the two in terms of division. And this will be our last step. So the first log expression would have its argument written as the numerator. And the log expression that's being subtracted would have its argument written as the denominator. And so we've completed this problem. We've written this original expression as one logarithmic expression. And that brings us to our last example for this section. We have ln, ln, and ln. So all of the bases of our logarithmic expressions are the same. Ln has a base of e. Okay, so we can combine all of these into one logarithmic expression. We can combine them all into one ln instead of having three separate ones. First thing you want to take care of are the factors in the front of the log, the 2 and the 5 in this case. We'll take the numbers in front of the logs and we'll rewrite them as the exponents of the argument. So with this last expression, we'll write 2y minus 1 to the 5th power. So after taking care of our exponents, now we use the property 1 and 2 to combine these into 1. Property 2 will take care of the first two. And when two log expressions are subtracted, we can rewrite them in terms of division with one log. And it's important to realize that the exponent 2 applies to not just the z or the 4 separately, but to this entire expression z plus 4. And now after combining the first two into one, we're left with two log expressions, and they're separated with the addition. And to combine them, we apply property 1, which simply says we take the two arguments of the separate log functions that are added and multiply them. So we could write this as log of x times 2y minus 1 to the 5th on top. And then since the ln of z plus 4 squared was subtracted, z plus 4 squared would go on the bottom in the denominator. And so that would complete this last example. We've rewritten these three original log expressions in terms of 1. So we're done.